Lesson 3.7 covers Gauss-Jordan elimination. We've already looked at a couple of ways to solve a system of equations. The first was the graphing method, where we graphed each line and determined the point where those two lines cross, which gave us our solution. The second was the addition-elimination method. This is where we got opposites as the coefficients for either one of our variables. We then added the equations together to eliminate that variable, solved for the remaining variable, plugged that back into the equation to find the other variable, and then we wrote that answer as an ordered pair. Now we're going to look at a third method, which is the Gauss-Jordan elimination method. Well, the Gauss-Jordan elimination method is a method that's commonly used by computers. This method is very helpful for large systems of equations. When I'm working the problems on my own, if I have a 2x2 system, a system with two equations and two unknowns, I'm probably going to use the addition-elimination method to solve it. However, if I have more than two equations or more than two variables, I go to the Gauss-Jordan elimination method. It's just a little bit easier to keep track of all the equations and variables. With the Gauss-Jordan elimination method, we're going to take a system of equations and create a system matrix or an augmented matrix. So suppose I have this example. My first equation is 2x plus y equals 3, and my second equation is x minus 3y equals 5. I want to create a system matrix. Well, my system matrix is going to look like this. Inside the matrix, my first row is a 2, 1, and then I have a vertical bar and I have a 3. My second row is 1, negative 3, and then I have a vertical bar and I have a 5. Well, let's look at these elements. The system matrix is composed of a coefficient matrix and a constant matrix. The 2, 1 in row 1 and the 1, negative 3 in row 2 were coefficients for my x's and y's. The 2, 1 were my x coefficients, and column 2, which is 1, negative 3, were my y coefficients. Well, I separate my coefficient matrix from my constant matrix with the vertical bar. On the other side of my vertical bar, I have a column that's 3, 5. Those were the constants for the equation. That vertical bar represents my equal sign. So the columns represent the coefficients and the constants. Now let's look at the rows. Row 1 represented my first equation, and row 2 represented my second equation. Well, when using the Gauss-Jordan elimination method, our goal is to get the right-hand side of that equal bar, which is my coefficient matrix, to become the identity matrix. On your screen, I have three different identity matrices. The first one is a 2x2 matrix, the second one is a 3x3, and the third one is a 4x4. Well, if you notice, there's a common theme to all of these matrices. First, the diagonal starting with the upper left-hand corner, the diagonal starting in row 1, column 1, contains all ones. So this is called the main diagonal. That main diagonal is going to contain ones every single time. So in each matrix, my main diagonal starting in row 1, column 1 contains all ones. Every other element is a 0. If that element is not on the main diagonal, it needs to be a 0. And as I've been saying, the diagonal containing the ones is referred to as the main diagonal. Well, when we're using the Gauss-Jordan elimination to solve, there's an order that we want to go in. So when solving using the Gauss-Jordan elimination, we're going to work column by column. You get the 1 first and then get all the zeros. You need to follow this order. Otherwise, if you put a 0 or a 1 in place, but it's not in the correct order, you may end up having to redo that step later in the problem. So let's look at some legal moves. How are we going to get those zeros and ones that we need? We can't just change a number to a 0 and 1. We've got to follow the math steps. So the first thing that we're allowed to do, we can switch any 2 rows. If you think back, the rows came from the equations that were in the system of equations. It doesn't matter what order that system of equations was given in, the solution is going to be the same. So when I set up a matrix, it doesn't matter the order that I put the rows in. The one thing I do want to keep in mind is if switching 2 rows changes a 0 and a 1, I don't want to move those 2 rows. So I really only like to switch rows in step 1, and if I'm careful, in step 2. Just kind of remember that once you put a 0 or a 1 in place, you don't want to switch the row that contains it if it changes that to another number. The second thing that I'm allowed to do, I'm allowed to multiply or divide any row by a number as long as it's not 0. Now, some books are picky and they don't like you to use the word divide with Gauss-Jordan or with matrices. But multiplying by a 1/2 is the same as dividing by 2. So it's just easier to go ahead and say we're going to divide by 2. But just keep that in mind if you're using a book. And finally, we can add any 2 rows together. So let's look at some examples of using these row operations. Our legal moves are called elementary row operations. So for the following system matrices, complete the given row operation. So I have this matrix where row 1 is 1, 7, 11, row 2 is 0, 6, 18. And I want to perform this operation. Well, this tells me the capital R's tell me where I'm going to put my answer. So my new row 2 is going to be found by taking the existing row 2 and dividing by 2. So that means my row 1 is not going to change. I'm going to only change row 2 because that's my capital R. I'm going to divide every number by 2. And like I said, some books don't like you to divide. They would say multiply by 1/2. But in this class, we're going to divide. So when I do this, as I said, row 1 is not going to be changed. I'm only changing row 2. Well, 0 divided by 2 is 0. 6 divided by 2 is 3. And 18 divided by 2 is 9. So my new row 2 is 0, 3, and 9. Now let's look at the next example. I have the matrix where row 1 is 7, 9, negative 2. Row 2 is 1, 10, negative 4. This time I want to perform the operation of switching or interchanging rows 1 and 2. That double arrow means I'm switching those 2 rows. If you remember our goal, we want our main diagonals to contain 1s. Well, row 2 already has a 1. So if I could rewrite this matrix where row 2 came first, I would have the 1 that I needed. So that's what this operation allows me to do. So I'm going to rewrite the matrix, and this time I'm going to list row 2 first. So my new row 1 becomes 1, 10, negative 4. And my new row 2 becomes the 7, 9, negative 2. Well, let's look at the next example. Row 1 is 1, 6, 4. Row 2 is 5, 2, negative 3. This time I'm going to do a combination of two steps. I'm going to multiply row 1 by -5, and then I'm going to add that result to row 2. And I'm going to put my answer in place of row 2. So the easiest way to do this is write this out. I'm going to first find -5 times row 1. Then I'm going to add row 2 to that. And this is going to become my new row 2. We'll multiply every element in row 1 by -5. -5 times 1 gives me -5. -5 times 6 gives me -30. And -5 times 4 gives me -20. Now I'm going to recopy row 2, which is 5, 2, -3. When I add these, -5 plus 5 is 0. -30 plus 2 is -28. And -20 minus 3 is -23. So since this was my new row 2, I'm not changing row 1. Row 1 is going to stay 1, 6, and 4. My row 2 is going to become 0, -28, -23. We generally only change one row at a time. Let's look at another example like this. This time I have a 3 by 4 matrix. My original system had 3 equations and 3 unknowns. So this time my new row 1 is found by multiplying row 2 by -7 and then adding that to row 1. So I want to first find -7 times row 2. I'm going to add row 1 to this, and this is going to give me my new row 1. So multiply every element in row 2 by -7. So 0 times -7 is 0. 1 times -7 is -7. 6 times -7 is -42. And -1 times -7 is 7. Now add this to row 1. Row 1 was 1, 7, -7, 10. So if I add this, 0 plus 1 is 1. -7 plus 7 is 0. -42 minus 7 is -49. And 7 plus 10 is 17. So my new row 1 is now 1, 0, -49, 17. This is the only row that's going to change. So when you rewrite the system matrix, leave rows 2 and 3 the same. And then fill in your new row 1. The 1, 0, -49, and 17. Let's look back at the second example. We talked about how we wanted the main diagonal to be a 1, and we noticed that row 2 had a 1. So we used one of our legal operations to switch the two rows, and that put a 1 in the main diagonal that we needed. So when we're wanting to get a 1, one way to get that is to switch two rows. Another way to get a 1 when we need it is to divide. If I didn't want to switch these two rows, I could look at the original matrix. There was a 7 where I wanted a 1 to be. I could change that to a 1 by dividing every number by a 7. The reason I chose not to do this is that would give me two fractions. I would have had a 9/7 and a -2/7. If I can avoid fractions, I'm going to try to do that. Now look back at example 3. In my original matrix, I had the 1 that I wanted. And then I mentioned before that we're going to work column by column, getting a 1 and then getting the zeros. So once I have the 1 in place, I want the elements below it to be a 0. So I needed to make this 5 become a 0. And that's what my row operation did. So let's look closely at what that row operation was. I multiplied -5 times row 1. Well, if you notice, the number that I multiplied by had the opposite sign of the number that I wanted to change to a 0. So you always take the number where you want the 0 to be and change its sign. We're going to multiply that by the row with the 1. And then we're going to add those two rows together. If you think back to the equations that this system came from, my first equation would have had a 1x, and my second equation would have had a 5x. And if you think back to the elimination method, and this is the Gauss-Jordan elimination method, so it's going to be similar to our addition elimination method we did in a previous lesson. If I had a 1x and a 5x, I would want those coefficients to be opposites. Well, we would get the opposites by multiplying the 1x by a -5 and then adding the equations together. That's exactly what I'm doing with this matrix. I'm just leaving out the variables. I want these two numbers to be opposites so that when I add them, I get a 0. So since I have a +5, I need the 1 to become a -5. So I multiplied that entire row by -5. I added it to the row I wanted to change, and that gave me the 0. Look at the last example. My first column has the 1, 0, 0 that I needed. My second column has the 1 in the middle, and then I would need the 7 and the -2 to both become zeros. Well, let's start with the 7. This is like having a 7y and a 1y. If I wanted to get those to eliminate, I'd need them to be opposites. Since I have a +7, I need that 1 to become a -7. I get it to become a -7 by multiplying the entire row by a -7. And then I add that to the row I want changed. And this gives me my new row with the 0 that I needed. So solving the matrix, getting the zeros and the ones are going to be similar to the system of equations that I solved with the addition elimination method. Before we move on to the examples, let me give you a few warnings about the Gauss-Jordan elimination method. It's not a complicated method if you pay attention to what I'm doing. Okay, the first two examples I suggest you just watch. Don't attempt to take notes. Put your pencils down and just watch what I do. As you watch the examples, think back to the addition elimination method because the steps are very similar. After you watch the first two examples, then rewind the lectures and take your notes then. If you attempt to take notes the first time through without watching what I'm doing, it's possible you're going to be completely lost. Don't expect to understand this method by watching the first example or even the second example. It's going to take you several examples to catch on to the steps. But once you catch on, the steps are very simple and they're very repetitive. There's only a few steps that you do, and you do these steps over and over. So let's look at the first example. I have the system x plus 4y equals 5 and -2x minus 5y equals -1. The first thing I'm going to do is write this as a system matrix. So row 1, I put in my coefficients and my constant. I have a 1, a 4, and a 5. In row 2, I have my coefficients -2, -5, and my constant -1. And you always put a vertical bar where your equal signs were. Now look to the left-hand side of the vertical bar. That's my coefficient matrix. I want that to become the 2 by 2 identity. So I always write my identity so that I see what I'm trying to find. With any identity matrix, the main diagonal is going to be 1s, and every other element is going to contain zeros. So I always work column by column. I want to work my first column first. You always get the 1 and then the 0. So look at the first column. I already have the 1 in place, so I just need to make this -2 become a 0. Well, think back to the addition-elimination method and look at your original equations. In my first equation, I had an x. In my second equation, I have a -2x. If I wanted those to eliminate, I would need this x to be a +2. So I would multiply row 1 by +2. I'm going to do the exact same thing with my matrix. I'm going to say +2 times row 1. Then I added the two equations together, so I'm going to do the same thing with my matrices. I'm going to add row 2. This is going to give me my new row 2. You always put your answer where you wanted that 0 to be. So 2 times row 1 gives me 2, 8, and 10. Then I recopy row 2, which is -2, -5, -1. 2 plus -2 gives me the 0 that I wanted. 8 minus 5 is 3, and 10 minus 1 is 9. This is my new row 2. Row 1 is not going to change. Even though I've temporarily multiplied row 1 by 2, in my matrix I want to keep it the same because it has that 1 that I want. So row 1 remains a 1, 4, 5, and my new row 2 becomes the 0, 3, 9. Now if I look back to my identity matrix, I wanted column 1 to be a 1 and a 0, and that's what I've got, is a 1 and a 0. Now I need column 2 to become a 0 and a 1 to match my identity matrix of 0 and 1. You always get your 1 first. I want this 3 to become a 1. Well, I don't have a 1 above it or below it to switch the rows like I did in my example. So the other way to get a 1 is to divide. I can divide that entire row by 3. So I'm going to take row 2 and divide every element by 3. When I do this, 0 divided by 3 is 0, 3 divided by 3 is 1, and 9 divided by 3 is 3. This is going to become my new row 2. So row 1 again is going to stay the same, and I'm just going to change row 2. So row 1 stays 1, 4, 5, and row 2 becomes 0, 1, 3. Now that I have my 1 in place, I want the 4 to become a 0. So think of this as a 4y and this as a 1y. In order for these to eliminate, I need to make the 1 become a -4. Since it's in row 2, I'm going to multiply row 2 by -4. Then I'm going to add the rows together. So I'm going to add row 1. And since I want to change row 1, this is going to become my new row 1. So -4 times row 2 gives me 0, -4, -12. Row 1 was 1, 4, and 5. Now if I add the 1 and the 0, I get a 1. If I add the -4 and the 4, I get the 0 that I wanted. And -12 plus 5 is -7. So this becomes row 1, and row 2 is going to stay the same. Now if you notice, on the left-hand side of my equal bar, I have my identity matrix. Once you have your identity matrix, your constants become your solutions. Basically, I have 1x plus 0y equals -7. So this is just x equals -7. So my -7 is my x value. In the second row, I have 0x plus 1y equals 3. So I just have y equals 3, so the 3 becomes my y value. Since this was a system of equations, I write this as the ordered pair -7, 3. Let's look at the next example. I have the system of equations 2x minus 4y equals -2 and 3x plus 2y equals 5. So let's begin by writing our system matrix. Row 1 is going to have 2, -4, -2. Row 2 will be 3, 2, and 5. My first column represents my x coefficients. My second column represents my y coefficients. I draw my equal bar, and my final column represents my constants. With my coefficient matrix, I have 2 rows and 2 columns, so I'm going to use my 2 by 2 identity. So we're going to work column by column, get the 1 first, and then the zeros. So I go to column 1, I want the 2 to become a 1, and then I want the 3 to become a 0. So let's begin with the 1. To make this 2 become a 1, I look below it and I don't have any 1s, so I can't switch my rows. Switching the rows will not help me. So the other way to make that 2 become a 1 is to divide. I need to divide every element in row 1 by 2. So my operation is row 1 divided by 2. If I divide row 1 by 2, this gives me a 1, a -2, and a -1. Since I wanted to change row 1, this is going to become my new row 1, and row 2 is going to stay the same. So row 1 becomes 1, -2, -1. And row 2 is going to stay a 3, a 2, 5. Now that I've got my 1 in place, I work on my 0. There's 2 steps to get your 0. We're going to first multiply and then add. Well, I take the number that's in place of the 0 and I change its sign. So I take that +3 and make it become a -3. And then I'm going to multiply it by the 1 that I just got, and that was in row 1. So I'm going to first start out, step 1 is -3 times row 1. Step 2 is to add this to the row you want changed. I want to change row 2, so I'm adding this to row 2. This is going to become my new row 2. So -3 times row 1 is -3, +6, +3. And then I add this to row 2, which is 3, 2, 5. Well, the -3 plus 3 gives me the 0 that I wanted. 6 plus 2 is 8, and 3 plus 5 is 8. So my new row 2 is going to become 0, 8, 8, and row 1 is going to stay 1, -2, -1. Now I have the 1 and the 0 in row 1 that I wanted. So I move on to row 2. Row 2 needs to become 0 and 1. Always get your 1 first. Look below it to see if you have any 1s, and I don't have any numbers below my 8, so I'm not going to be able to switch rows. So the other way to get a 1 is to divide. I'm going to divide that entire row by an 8. Well, row 2 divided by 8 gives me 0, 1, and 1. This is going to become my new row 2, and row 1 is not going to change. So row 1 stays 1, -2, -1. Row 2 became 0, 1, and 1. Now that I have my 1 in place, I need this -2 to become a 0. Well, to make this become a 0, change its sign to a +2 and multiply by the row that contains the 1 you just got. So I'm going to say 2 times row 2. And then I add this to the row I want changed. I want to change row 1, so I'm going to add this to row 1. And this is going to become my new row 1. So 2 times row 2 is 0, 2, and 2. Row 1 was 1, -2, -1. Now I'm wanting to change row 1. Row 1 had a 1 in place, and I do not want it to change. If you notice, if I add 0 plus 1, I keep that 1 that I didn't want to change. If that 1 changed, then you did your step wrong. The next element was a -2. I wanted it to become a 0. Well, 2 minus 2 gave me the 0 that I wanted. And then finally, I have 2 minus 1 is 1. So my new row 1 is 1, 0, 1. And row 2 stays the same, 0, 1, 1. Now if you notice, to the left of the equal bar, I have my identity matrix. I have the diagonal 1s and the 0s everywhere else. When you have the identity matrix, your constants become your solutions. So my first value is the solution for x, so x equals 1. My second value is the solution for y, so y equals 1. So my solution is the ordered pair 1, 1. Let's look at the next example. My first equation is 3x minus y equals 2. My second equation is x plus 2y equals 10. First, I want to write this as a system matrix. So I have 3, -1, 2, and 1, 2, 10. Since I have a 2 by 2 matrix in front of my equal bar, I want to use the identity for a 2 by 2 matrix. So I want the 3 to become a 1, and I want the 1 to become a 0. You always get your 1 first and then the zeros. Well, I need this 3 to become a 1. Look below it to see if you have a 1, and we do. So since I'm just starting out, I haven't put any 1s or 0s in place. So I can switch these two rows if I want to, and that's exactly what I'm going to do. I'm going to interchange, or I'm going to switch rows 1 and 2. So my new system matrix becomes 1, 2, 10 for row 1, and row 2 is now 3, -1, 2. So this allowed me to get the 1 in place without dividing. Now I need the 3 to become a 0. So change its sign to a -3. Multiply by row 1 because row 1 has the 1 that I just put in place. So I'm going to start with -3 times row 1. Well, -3 times row 1 is -3, -6, -30. I'm going to add this to the row I want changed, which is row 2. Row 2 is 3, -1, 2. This is going to give me my new row 2. So -3 plus 3 gives me the 0 that I wanted. -6 minus 1 is -7. And -30 plus 2 is -28. So row 1 stays the same, 1, 2, 10. And row 2 becomes 0, -7, -28. Now I have column 1 exactly as I need it. I move on to column 2. I get my 1 first, so I need this -7 to become a 1. There's no numbers below it, so I'm not going to switch the two rows. If I switched these two rows, that would mess up my 1 and my 0 in column 1. So to make this negative 7 become a 1, I'm going to divide row 2 by negative 7. Well, if I divide row 2 by negative 7, I get 0, 1, and 4. This is going to become my new row 2, and row 1 is going to stay the same. So row 1 stays 1, 2, 10, and row 2 becomes 0, 1, and 4. Now that I have my 1, I need the 2 to become a 0. So change its sign to a negative 2 and multiply it by the row that contains the 1 that I just put in place. So it's negative 2 times row 2. Negative 2 times row 2 is 0, negative 2, negative 8. Now you always add this to the row you want changed. I want to change row 1, which is 1, 2, and 10. This is going to become my new row 1. Well, row 1 contained a 1 that I did not want to change. So if I look, when I add the 0 and the 1, I get the 1. So that did not change. The second number I wanted to be a 0. Well, the negative 2 plus the 2 gave me the 0 that I wanted. And then finally, I have negative 8 plus 10 is 2. So my new row 1 becomes 1, 0, 2, and row 2 stays 0, 1, 4. Now that I have the identity matrix to the left of my equal bar, my constants give me my solutions. So x is a 2 and my y is a 4. So my solution is the ordered pair 2, 4. Let's look at our next example. This is a system with 3 equations and 3 unknowns. So let's begin by writing our system matrix. Row 1, I use the 3, the 8, the negative 1, and then on the other side of my equal bar, I have a negative 18. Row 2, my coefficients are 1, 2, and 1, and my constant is a negative 2. For row 3, my coefficients are 2, 1, and 5, and my constant is an 8. Well, if you look at your coefficient matrix, it's a 3 by 3. So for my identity matrix, I need a 3 by 3 matrix. The main diagonal contains all 1s, and there's zeros everywhere else. So just like with the 2 by 2 systems, we're going to work column by column, get our 1 and then our zeros. Since this example has more equations and more variables, we're just going to have more steps, but the steps are identical to the other examples. So let's begin with column 1. I want to get a 1 in row 1, column 1. So I need this 3 to become a 1. Well, look below it and I have a 1. So it didn't matter what order these equations were given in. When I graph them, I'm going to get the same solution. It doesn't matter which one I graph first or second or third. So it didn't matter which order the equations were listed in. That allows me to switch 2 rows in my matrix. So I'm going to switch rows 1 and row 2. So when I do this, row 1 becomes 1, 2, 1, negative 2. And row 2 becomes 3, 8, negative 1, negative 18. And row 3 stayed the same, 2, 1, 5, 8. Now that I have my 1, I want the 3 and the 2 to both become zeros. Now you can do these as separate steps or you can do this as the same step. It doesn't matter. But we're going to do one at a time. So let's first work with the 3. Change its sign to a negative 3. and multiply by the row with the 1 that's above it. So I'm going to say negative 3 times row 1. Well, negative 3 times row 1 is negative 3, negative 6, negative 3, positive 6. Next, I'm going to add the row I want changed. I'm wanting to change row 2, so I'm adding row 2. Row 2 is 3, 8, negative 1, negative 18. This is going to give me my new row 2. Well, negative 3 plus 3 gives me the 0 that I wanted. Then negative 6 plus 8 is 2. Negative 3 minus 1 is negative 4. And 6 minus 18 is negative 12. So now rows 1 and 3 stayed the same, and row 2 became 0, 2, negative 4, negative 12. Now, if you know that you're going to change row 3, if you wanted to leave that blank and go ahead and change it to save you from writing the matrix again, you can. In the solutions to the homework problems, I do get these 2 zeros before I rewrite my matrix. So it doesn't matter if you rewrite your matrix now or after you get the next 0. So let's look at making this 2 become a 0. Change its sign to a negative 2 and multiply by the row containing the 1 that you put in place. So I'm going to multiply negative 2 times row 1, and this gives me negative 2, negative 4, negative 2, positive 4. I'm going to add the row that I want to change. I want to change row 3, which is 2, 1, 5, and 8. This is going to become my new row 3. So negative 2 plus 2 gives me the 0 that I wanted. Negative 4 plus 1 is negative 3. Negative 2 plus 5 is 3. 4 plus 8 is 12. So rewrite your matrix, keep rows 1 and 2 the same, and now make row 3 become 0, negative 3, 3, 12. Now look back to the identity matrix. We've completed column 1. We have the 1 and the 2 zeros in place. So let's mark it out and move on to column 2. I want the 1 to be in the middle and a 0 above it and a 0 below it. So I need the 2 in row 2 to become a 1. In order to do this, I look below it to see if I have a 1, and I do not. So the easiest way to make this 2 become a 1 is to divide every element in row 2 by 2. If I divide row 2 by 2, I get 0, 1, negative 2, negative 6. This is going to become my new row 2, and rows 1 and 3 are going to stay the same. So rows 1 and 3 stays the same, and row 2 becomes 0, 1, negative 2, negative 6. Now I need the 2 and the negative 3 to become zeros. It doesn't matter which one you do first, and you could do both steps and then rewrite your matrix if you want. So let's start with the 2. Change its sign to a negative 2 and multiply by the 1 that you just put in place, which is in row 2. So negative 2 times row 2. Negative 2 times row 2 gives me 0, negative 2, 4, and 12. I add this to the row I want to change. I want to change row 1, which is 1, 2, 1, negative 2. This is going to give me my new row 1. Now row 1 started with a 1, and it should not change. 0 plus 1 gives me the 1 that I did not want to change. Then negative 2 plus 2 gives me the 0 that I wanted. Then 4 plus 1 is 5, and 12 minus 2 is 10. So I can write this as row 1 and keep rows 2 and 3 the same. Next, I want the -3 to become a 0. So change its sign to a +3 and multiply by the row within that same column that has the 1. So I'm going to say 3 times row 2. 3 times row 2 is 0, 3, -6, -18. Then I'm going to add this to the row I want to change, which is row 3. Row 3 is 0, -3, 3, 12. This is going to become my new row 3. Well, row 3 started with a 0, which I did not want to change. And if you look, my first elements, I have 0 plus 0 gives me the 0, so it did not change. Then next, I wanted that -3 to become a 0. Well, 3 minus 3 did give me the 0 that I wanted. Then -6 plus 3 is -3, and -18 plus 12 is -6. So this becomes your row 3, and you keep rows 1 and 2 the same. So now look back at the identity matrix. It's at the top of your page. We've completed column 1, and now we've completed column 2. So let's move on to column 3. I want column 3 to have a 0, and a 1, but I always get the 1 first. So I need this -3 to become a 1. Look below it to see if you have any 1s. The reason I always look below it is I don't want to look above. I don't want to switch these 2 rows with anything because I've put those 1s in place. If I switch these 2 rows, it messes up my 1s. So always look below it. I don't have any elements below it, so I can't get a 1 by switching the rows. So to get a 1, I'm going to divide row 3 by a -3. Well, if I divide row 3 by a -3, I get 0, 0, 1, 2. This is going to replace my row 3. Rows 1 and 2 are going to stay the same. So now that I have the 1 in place, I want the 5 and the -2 to become zeros. Let's start with the 5. Change its sign to a -5 and multiply by the 1 that I just put in place. You want the 1 in that same column. So I'm going to say -5 times row 3, because for column 3, the diagonal 1 is in row 3. Well, -5 times row 3 gives me 0, 0, -5, -10. I'm wanting to change row 1, so I add this to row 1, which is 1, 0, 5, and 10. This is going to become my new row 1. Well, if you notice, row 1 starts with a 1 and a 0, and I do not want those to change. So if I add 0 plus 1, I get my 1. 0 plus 0, I get the 0. So they did not change. If those had changed, you did your step wrong. Next, I wanted the 5 to become a 0. Well, -5 plus 5 gives me the 0 that I wanted. And then I have -10 plus 10 is also a 0. So my new row 1 becomes 1, 0, 0, 0. And keep rows 2 and 3 the same. Now for my final step, I need this -2 to become a 0. So change its sign to a +2 and multiply by the 1 that's in row 3. Well, 2 times row 3 gives me 0, 0, 2, 4. I'm wanting to change row 2, so I add row 2, which is 0, 1, negative 2, negative 6. This is going to give me my new row 2. Well, row 2 started out with a 0 and a 1, and I do not want these to change. Well, 0 plus 0 is 0, and 0 plus 1 is 1. So my 0, 1 did stay the same. Next, I wanted the negative 2 to become a 0. Well, 2 minus 2 gives me the 0 that I wanted. And then finally, 4 minus 6 gives me a negative 2. So replace row 2 with 0, 1, 0, negative 2, and keep rows 1 and 3 the same. Now if I look to the left of my equal bar, I have the identity matrix for a 3 by 3 matrix. So now I look at my constants, which give me my solutions. This time I have 3. If you remember, the equation had an x, a y, and a z. My first value of 0 is my x, my negative 2 is my y, and my positive 2 is my z. This time, instead of writing my solution as an ordered pair with 2 numbers, I write it as an ordered triple with 3 numbers. So my solution is the ordered triple 0, negative 2, 2. Now let's look at our final system. I have x minus y equals 6, 2x minus 2z equals 16, and 2y plus z equals 8. I have 3 equations and 3 unknowns. If you notice with this example, each equation has a variable missing. The first equation does not have a z, the second equation does not have a y, and the third equation does not have an x. So be really careful when you're creating your system matrix. It's a little bit easier if you go ahead and fill in the missing variables with zeros. So I said the first equation did not have a z, so that's like adding in a plus 0z. And for the second equation, put in a plus 0y. And for the third equation, it's like having a 0x. Now I can easily pull out those numbers to put in my system matrix. So row 1 is 1, negative 1, 0, 6. Row 2 is 2, 0, negative 2, 16. And row 3 is 0, 2, 1, 8. Remember, column 1 had to be my x coefficients, column 2 had to be my y coefficients, and column 3 had to be my z coefficients. Looking at the original system, it looks like I just have 2 columns. I can't let column 1 in my system matrix be a 1, 2, 2 because that second 2 is a y value, so it needed to go in column 2. That's why it was easier to fill in my zeros. So now I can take the coefficients 1, 2, 0 to become my x column, 1, 2, 0. So I need the identity matrix for a 3 by 3. So begin with column 1. I want to get my 1 and then my zeros. Well, in this equation, I already have a 1 where I need it to be. So I just need to get the zeros below it. I already have one of those zeros, so I just need to find the other 0. I need this 2 to become a 0. So change its sign to a negative 2 and multiply the 1 that's in that same column, which is in row 1. So negative 2 times row 1 gives me negative 2, 2, 0, negative 12. I add this to the row I want changed, which is row 2. Row 2 is 2, 0, negative 2, 16. This is going to give me my new row 2. Well, in my new row 2, negative 2 plus 2 gives me the 0 that I wanted. 2 plus 0 is 2. 0 minus 2 is negative 2. And negative 12 plus 16 is 4. So this becomes my new row 2. So replace row 2 with 0, 2, negative 2, 4. And keep rows 1 and 3 the same. Now if I look back at my identity matrix, I have column 1 exactly as I want it, so I move on to column 2. I need the second number in that column to be a 1. So I need to change this 2 to a 1. Now if I look above it, I have a negative 1. Even if that had been a positive 1, I do not want to switch these two rows because it would mess up the 1 and the 0 for column 1. So always look below it for a 1, and I don't have a 1 below it. So I'm going to make this be a 1 by dividing. So I'm going to divide row 2 by 2. When I do this, I get 0, 1, negative 1, 2. So keep rows 1 and 3 the same and replace row 2 with 0, 1, negative 1, 2. Now I need the negative 1 and the 2 to become zeros. So let's start with the negative 1. Change its sign to a positive 1 and multiply it by the 1 that's in row 2. So I've got 1 times row 2, or just row 2. That gives me 0, 1, negative 1, 2. Now add this to the row you want changed, which is row 1. Row 1 was 1, negative 1, 0, 6. This is going to become my new row 1. So 0 plus 1 is 1. 1 minus 1 is 0. Negative 1 plus 0 is negative 1. And 2 plus 6 is 8. So rewrite this for row 1 and keep rows 2 and 3 the same. Now I want the 2 to become a 0. So change its sign to a negative 2. Multiply by the 1 that's in row 2. So I have negative 2 times row 2, which is 0, negative 2, 2, negative 4. Now I'm going to add this to the row I want changed, which is row 3. And that's 0, 2, 1, 8. This is going to give me my new row 3, which is 0 plus 0 is 0. Negative 2 plus 2 is the 0 that I wanted. 2 plus 1 is 3. And negative 4 plus 8 is 4. So replace row 3 with 0, 0, 3, 4. And keep rows 1 and 2 the same. Now if you look back at the top of your page, you have the identity matrix for a 3 by 3. We already completed column 1 and it did not change. And now we've completed column 2. So we move on to column 3. I want to get the 1 first and then the zeros. So I want to make this 3 become a 1. I can't use the 1s above it because that would mess up my diagonal 1s. So I have to change this 3 to a 1 by dividing. I'm going to say row 3 divided by 3. When I do this, I have 0, 0, 1, and 4/3. Always use fractions. Don't ever use decimals with these Gauss-Jordan problems. Especially with 4/3, that would give you a repeating decimal. You want to keep it a fraction to keep it accurate. So replace row 3 with 0, 0, 1, 4/3 and keep rows 1 and 2 the same. Now I want both of my negative 1's to become a 0. So let's start with the first one. Change its sign to a positive 1 and multiply it by the 1 in row 3. So I'm going to have 1 times row 3, which is just row 3. Row 3 was 0, 0, 1, 4/3. Now I want to change row 1, so I'm going to add row 1 to this. Row 1 was 1, 0, negative 1, 8. This is going to become my new row 1. So 0 plus 1 is 1. 0 plus 0 is 0. 1 minus 1 is the 0 that I wanted. And 4/3 plus 8 is 28/3. You can add these fractions on your calculator. Just be sure you give your answer as an improper fraction. Don't ever give your answers as decimals, and don't ever give your answers as mixed numbers. So replace row 1 with 1, 0, 0, 28/3 and keep rows 2 and 3 the same. Now for my final step, I need the negative 1 to become a 0. So change its sign to a positive 1 and multiply by the 1 in row 3. So 1 times row 3 is just row 3, which is 0, 0, 1, 4/3. I want to change row 2, so I'm going to add row 2, which is 0, 1, negative 1, 2. This is going to become my new row 2. So my new row 2, 0 plus 0 is 0. 0 plus 1 is 1. 1 minus 1 is 0, and 4/3 plus 2 is 10/3. So change row 2, but keep rows 1 and 3 the same. Now I have the identity matrix for my coefficient matrix. So I can look at my constants to get my solutions. So x equals 28/3, y equals 10/3, and z equals 4/3. So I write this as an ordered triple: 28/3, 10/3, and 4/3.